So today we will talk about an alternative data structure. Okay, so that's called navigating nets. Okay, so I can tell you this is a famous data structure in theoretical computer science. Okay, I would have to say it's a little surprising that I do not see any implementation of this data structure in the database community. Okay, to the best of my knowledge. Okay, and as you will see today, I will present a simplified version of the data structure so that you can see the core ideas. Okay, and this data structure actually achieves performance that proximity graphs cannot achieve. Okay, so that's something interesting. Okay, so I think there is something to be explored here, because on the one hand, as I said, if you look at things from the perspective of metric spaces, okay, and I will explain, as I'll explain later, this navigating net is able to achieve performance guarantees that are beyond the reach of proximity graphs. Okay, and on the other hand, to the best of my knowledge, I did not see any implementation and comparison to this data structure. Okay, and this data structure is not that complicated. Actually, it's quite simple. At least the version that I'm going to present today is quite simple. Okay, and if you still remember the proximity graph that I introduced last week, you will see a lot of similarity between that proximity graph and the structure that I will present today. Okay, so this is my opening monologue for today. And at the end of today's talk, I'll come back to the points that I made. All right, so at that point, I think we will be in a better position to look at those points in more detail. Well, as usual, I'm going to denote the metric space, as a pair. This is M, okay, M and D, okay, M and D, right? So M is a set, and D is the distance function, okay? So this lambda, so here this lambda is the doubling dimension, okay? Okay, that's okay, don't worry. Please mute yourself. All right, so this doubling dimension is assumed to be a constant, okay? So this is the scenario I'll focus on. And now we've got a P. So this is a data set. And this data set has a size of N, okay? So this is also the same as before, right? Now, without loss of generality, we'll assume that the smallest interpoint distance in P to be 2. Okay, so we saw the same thing last week, and we don't lose any generality here because what you can do is to scale the distance function accordingly, right? If this is not the case, and this is really just for simplification, okay, for our convenience in our technical discussion later. Okay. You still remember this function, right? So this is the diameter. Okay, so this diameter is defined as the largest interpoint distance in P. Okay, so this is called the diameter of the data set. All right. So something else we still need is this aspect ratio. All right, so this aspect ratio is defined as the ratio between the maximum interpoint distance and the smallest interpoint distance, right? So in our case, it's defined as the diameter divided by 2. Okay, so this is the setup. So today I will talk about 3 A and N. So in other words, if you want to relate this to 1 plus epsilon A and N, then essentially epsilon is 2. Okay, epsilon is 2. I would say this will allow you to see the underlying ideas of this navigating net. Okay, this navigating net can be adapted to support any value of epsilon. Okay, however, the full version will not be as simple as I will present. Okay, it will be something more complicated. I think it's very important to get the main ideas first. All right, so then you can, if you want, you can go and read the paper. Presenting this navigating net is the first purpose. Okay, but there's another very important purpose I aim to achieve today. So last time I introduced this very important concept of RNet. Okay, so still remember what I said, right? I said RNet is a very fundamental tool for you to design algorithms in metric spaces. Okay, please take my word for it. Okay, so to be honest, in my memory, right, I don't remember having seen a single non-trivial problem that can be solved without using RNet. All right, so just think about RNet as something that you must be able to be familiar with if it makes sense for you to start thinking about how to solve a metric space problem efficiently, right? So otherwise you're missing out on a very important tool. And this is just like you want to deal with sets of integers without knowing binary search tree. So I mean, there is an obvious vulnerability in your knowledge, right? So in general, if you want to reason with metric space object data, RNet is something extremely helpful. Okay, so I mean, this topic has gone through a lot of research, and people have devised a lot of proved a lot of lemmas and theorems on RNets. So those results, they're so rich, right? And they are at your disposal. You see what I'm saying? You can use them immediately. So that's why, right? So you are standing on the shoulders of giants. All right, so we've got this RNet. Still remember what that is, right? So it simply says, let me give you an example, right? So it simply says, let's say if this is your data set, okay? And let's say the distance of R is, this much, okay? So let's say this is distance of R, okay? And then basically RNet says you don't really need to remember all the points if you want to have a good summary, okay, of the distribution of the data set, okay? Now this summary will have to be at the order of R, okay? So at a very high level, that's the idea, okay? So last time I explained the general idea behind the computation of RNets, right? So what you can do is, you start with an arbitrary point and you say, I want to include this point, right? And then you want to look at the point, you want to identify the point with the largest Macdonald distance, right? So you've got only one Macdonald here. So this will be the second point you want to include into the RNet, right? So, and then you want to identify the next point with the largest Macdonald distance, right? So I think looks like, this would be the point, okay? So this point has the largest Macdonald distance so far. So 3 points in the RNet already, and you want to continue doing this. So I guess this will be the next guy, right? So if you continue doing that, I think this will be the next one. If I want to include the next one, I guess it will be here, and then here. Okay. So at this point, I can stop. Why? Because if you look at the next point, with the largest McDonald distance at the moment. Sorry. So I would say maybe this would be the guy, right? But this guy's McDonald distance is already less than or equal to R. You see what I'm saying? So you don't have to include this point into the RNet anymore. And you know that the points that I have selected, they have a very important purpose. They have very important property, okay? So the property is every point that I have not selected is within distance R to at least one point that I have already selected. You see what I'm saying? Okay. So if you look at the points that I have chosen, you know these points, their interdistance is greater than R. You see what I'm saying? Okay, because I stopped the whole algorithm as soon as the McDonald distance drops below this R, right? Okay, these two properties are the two very important properties of RNets. Okay, so let's summarize those two properties, right? The first one is separation. Okay, separation. So the separation property says, for any, let's say P1, P2 in the RNet, you definitely have, the distance between them is at least R. Okay. Well, you would say the points I chose is strictly larger than R. Yeah, sure, that's correct, but separation property is a little weaker, okay? So covering property, so it says for any point, let's say Q, okay, in the data set, okay, definitely there is a point, let's say Y. Okay, you know what, let's be consistent. I'll use Y to refer to points in an RNet. Let's say this RNet is big Y, okay. All right. So here, there definitely is a point that I have already chosen such that the distance from this Y to your Q is some point in the data set, okay, not in the metric space, in the data set, okay. So this is bounded by R, okay. So this is the separation property and also the covering property. Okay, good, very nice. All right, so now we are ready to define the data structure. So the data structure is very simple. It says, look, if you look at the distance range, right? It goes from, so the largest distance range is, that I'm interested in is at the level of the diameter. You see what I mean? And the smallest one would be something like 1, okay? The interpoint distance is 2, right? So intuitively, if you look at the spectrum of this distance range, right? Intuitively, it goes from, say, 1 all the way to the diameter of the data set, okay? So what I'm going to do is I will, take the log of this diameter of the data set, P, okay? So, 2 to the power of H is larger than or equal to the diameter, okay? So we use a trick that, you saw that we use a trick that we already used the last time, okay? So we cut this spectrum of distance, right? This distance spectrum into increasingly longer intervals. You see what I mean? Okay. So basically, I want to have some sentinel points, in this spectrum. I'll be considering some very special values of R, okay, and powers of 2. Okay, so I'll be considering 2 to the power of 0, 2 to the power of 1, to the power of 2, all the way to the power of H. Okay. So by selecting these values, essentially, I am chopping off this distance range from 1 to the power of H into intervals, right? Into um, a number of intervals. Okay. Now, here, one thing I'm going to do is for every value of r, okay, so I will compute an r net. Okay, so this is 2 to the power of I net. Okay, so I do this for every I. Okay, so I goes from 0 to h. You see what I mean? Okay, so this is what I do. All right. So overall, you can, I mean, so far, by the way, I have not explained the whole data structure. Okay, but so far, what you can imagine is that I have different summaries of the original data set. Okay, and each summary is at a different distance scale. You see what I mean? Okay, so that's what I have done so far. Now let's look at these summaries. Okay, so there are several things we should know. So first of all, if I say y0, so what should be y0? Okay, now think about it. Y0 essentially says it's a one net. Okay, it's one net of your data set. You see what I mean? One net, right? So you should have points like the circle points, except that this time the covering property says, right, every point that you have not selected will have to be within distance 1 from some point that you have selected. You see what I mean? Okay. But wait, that's not quite possible. You see what I mean? Because I said before, right, the smallest inter-point distance is defined to be 2, right? So that's the reason why I needed that. Okay. And therefore, want each point to be covered. Let's say you are a point, right? You want yourself to be covered. You cannot really rely on finding, another point, and this point's distance is at most 1 from you. That's not possible because you cannot find such kind of points at all, right? And therefore, if you want to get yourself covered, there's only one possibility. You will have to get selected. You see what I'm saying? Okay. So if I say, what is the one net of P? Well, it's very simple. The one net of P is just P itself. Okay, it's just P itself. All right, good. And this is one extreme. You see what I mean? Now let's look at the other extreme. What is YH? Okay. Now remember, YH is the 2 to the power of H net, right? But 2 to the power of H is even greater. I mean, at least the diameter, right? At least the diameter. Now, I argue that you have only one guy in your net, all right? So one point that you can circle. You see what I mean? Well, if you don't agree, and then you give me 2 points, and then I will say, these 2 points, they will have to get separated. You see what I mean? So their distance will have to be at least 2 to the power of H, right? Okay, so maybe I was not entirely correct because you can argue with me. Okay, if the diameter is exactly 2 to the power of H, then yes, you could have multiple points, okay? And then in that case, okay, I will need one more net, okay? So today, let's just assume, for my convenience, that the diameter of P is not a power of 2. You see what I mean? So in this case, I would say this YH has just one single point, right? Because 2 to the power of H this time is strictly larger than the diameter of P. You see what I mean? Okay. If that's not the case, I would just increase this H by 1 more, okay, so that I can achieve that purpose. So what I need is, this YH to have just one single point, okay? All right, so naturally you wonder what happens to the size of every other net. You see what I mean? So if I say yi net, and then this is a 2 to the power of I net. You see what I mean? Okay, so the scale of this R is 2 to the power of I, right? By the way, now remember all those values of R chosen, right? So it doubles each time, okay? It doubles each time. This doubling trick is not surprising at all, right? Because, oftentimes this is how you deal with, a continuous problem, right? So you want to chop it up into such kind of, discrete granularity, right? Such kind of, This technique is very usual, right? Very normal. So as I was saying, you have every right to wonder what happens to the size of this yi, right? So I think in practice, it would be reasonable to say, as the value of I, as the value of I increases, and then the size of this yi is going to tend to be smaller and smaller, right? So that's something nice about these nets. However, in theory, we have to be very conservative, right? In theory, the only thing we can say is that its size is always bounded by n, right? Because obviously, even in the worst case, what you can do is to choose all the points, right? You cannot do worse than that, okay? All right, so now I have all these nets, okay? All these nets. Now I will get them connected, okay? Connected, all right? So what's gonna happen is you can imagine I place all these nets at different levels, all right? So the highest level is level H, right? So YH contains just a single point there, okay? So it's just a single point here. Now, YH minus 1, I don't know. It could contain n points if we're not lucky, right? But I don't care, right? So you simply lay out all the points, at the next level, okay? I have not explained how points of different levels get connected, okay? I have not explained anything about that, all right? What I'm just saying is that you imagine that points are placed at different levels like this, okay? So you do that to every single level. So basically, you have H plus 1 levels, okay, good. Now I'm ready to explain how to get the points connected, right? So first of all, let me tell you, you are not gonna get a tree, okay? So if I started with something like this, I guess maybe it appears as if I was going to define something like a binary tree, okay? No, okay, you're not gonna get a tree, you're gonna get a graph, okay? So what's the difference between tree and graph? Well, a tree, right? So a tree is like a graph without any cycles, right? But you could have cycles, right? Although here it's going to be a directed graph. So you don't really get cycle, but it's not a tree as you will see, okay? Because a tree, every guy will have just one parent, right? But as you will see, this is not the case here, okay? So let me tell you how to do the connections in general, right? So I will keep the discussion general, and I will say, look at a point, let's call it Y. Let's look at a point in some level, right? So let's say yi. All right, so this is a point in yi, okay? Now, quick question. So yi, what is the value of r for yi? Don't say I, okay? It's 2 to the power of I. You see what I'm saying? Okay, 2 to the power of I, good. All right, so now you look at a point z, and this point z is from the next level, okay? So this is from y I minus 1, all right? Now, I have many y's at level I, many z's at level I minus 1, right? I do not really have full connection. You see what I'm saying? Okay. I will connect a y to a z only if the following condition holds. Okay, the condition says the distance from y to z is less than 7 times to the power of I. Okay, all right. So let's look at this for a little longer. All right, let's get some intuition. All right. So first of all, you can see this is something that depends on I. Okay, this is not too surprising, right? Especially when you see 2 to the power of I, you should not get very surprised. You see what I'm saying? Because I asked you this question, right? I said, okay, now we're talking about level I here. So what should be the distance granularity? You see what I'm saying? Okay. So the distance granularity is 2 to the power of I, right? So there you go, right? You see the 2 to the power of I there. Of course, you have every right to wonder how did I get this 7, right? Well, in theory, oftentimes we need to have some constants, right? So these constants might look like magic constants at first place, but they serve important purposes in the analysis, right? So in general, when you design a data structure, it's actually a backward process. You see what I'm saying? Let's say you there's some constant that you have to leave open here, and then you don't fix it right now, and then you just do the analysis anyway with this let's say constant C, right? And then you look at the constraints that this C must satisfy for your argument to work, right? And then hopefully, when you solve this C from those constraints, you get some working value. You see what I mean? Okay. So it turns out that this 7 works. Okay. And we will see why later. All right. So if you set it to something smaller, I'm not sure. Okay. I don't think it will work. But anything larger, it will work. Okay. All right. Now, why do we want to do this? Okay. Why do we want to connect this Y, small y, to such a Z, right? So this is not too surprising either. You see what I'm saying? Because this is like if you have a summary at a larger granularity, a coarser granularity. That's what I mean, coarser, right? Granularity to the power of I, right? And then you would like to provide some guidance to the next level. You see what I'm saying? Okay. So what would be reasonable guidance here, right? So I would say this is like, okay, if you already know that I am in Singapore already, okay? Now, if you want to go to Jurong Point, okay, so I can point you to Jurong Point. You see what I'm saying? All right. But I'm not going to say I'm in Singapore already, but I will keep an edge to New York. You see what I'm saying? So I assume since you have already shown interest in me, shown interest in this Y, right? So I assume that you would like to explore the vicinity of Y. Okay, so that's why I give you more pointers. Okay, I give you more pointers to the vicinity. Actually, as you can see, the vicinity is chosen to be 7 times to the power of I, right? So that feels a reasonable thing to do, right? Okay. All right, so if you do this, and then you have the data structure. You see what I mean? Okay, so you can imagine if you do this, you will get something like a graph. This is not a tree. Why? Because this Z may not have just a single parent. You see what I mean? Okay, and so in general, you can imagine this as a multi-level structure, and that is true. Okay, so the first level, the highest level is level H. There can be only one guy at level H, right? So that will be the starting point for our query algorithm later. But then as you move down, you will see it's really, really a graph, right? So think about it as a directed graph, and then so that you don't have cycles, right? So all the edges are pointing downwards, right? Okay, good. That's the algorithm. If you still remember the proximity graph that I introduced last time based on RNets, I guess at this point you should start to feel some similarity is there. Okay. Anyway, that's not important for today. Good. All right, and then that's the data structure. Very simple, right? Very simple, right? Okay, I think you can implement it tonight to see what happens, right? Now, query. How can we answer a query? Okay, well, extremely simple. Extremely simple. You start from the root. Okay, well, what do I mean by root here? I guess that's obvious, right? So the only guy, yeah, in YH. All right. So you take the out neighbors. Okay, you look at the out neighbors. Oh, by the way, let's introduce some convenient terminology. Okay, so this Z, I will call it a child of Y and a child of Y prime. You see what I mean? This is very intuitive, right? Okay, but this is not a tree. Okay, let me emphasize. All right, so this can be a child of a lot of parents. Okay, maybe M parents. That's possible. Okay, good. All right, so now I can say, look at the query algorithm. You look at the root, and then you look at all the children. All of them. Yes, you spend time looking at all the children of the root, all right? And then you want to go greedy. Sounds familiar, right? Hey, sounds familiar, right? You want to go greedy, okay? So you want to identify the child closest to the query point. Is that clear? All right, good. So that will allow you to move one level down, okay? Repeat, all right, repeat. You see what I'm saying? So at the next level, again, you look at the children of that point, and then you go for the child closest to the query point. So you do this, at all levels, right? So you can only go down. You see what I mean? You can never go up because all the edges are pointing down, right? So in this case, eventually you will get to the 0 level and then you stop there, right? Okay. So at this point, you have accessed exactly h plus 1 points, right? Starting from, 1 per level, right? So it's a single path in this graph. You see what I'm saying? A single path in this graph. Good. All right. So you want to return the best point on the path. You see what I'm saying? All right. Now here are some common misconception, some common confusion at this moment is that, well, the lower the better. Okay, so maybe I should return the point from level 0. Okay, not necessarily. All right, not necessarily. All right, this is something interesting. All right, and it doesn't work like that. All right, it's not like as you descend, you always get better results. All right, not necessarily. But what I'm saying is you look at the h plus 1 points you have collected on the path. Okay, and by the way, along the way, you have already calculated their distances to the query point, right? Okay, now return the best out of those h plus 1 points. And that's the algorithm. That's it. Okay, that's it. All right. So now let's look at the most interesting part, the analysis, right? The analysis is always the most interesting part, right? Why does this work, right? Okay. So first of all, let's understand why the space consumption is small. Okay, why the space consumption is small. Look, at every level, as I said, right? You have to be prepared for the worst case, right? So in the worst case, at every level, other than the highest level, every other level would have endpoints. You see what I mean? Okay. So you have to record those endpoints, but in addition to that, you also have to record their children. You see what I'm saying? So basically, it's the number of edges that matters, right? It's the number of edges that matters. So next, I'm going to show you that every point has only a constant number of children, okay? Constant number of children. So essentially, it says every point I have only a constant number of edges going to the next level, right? So if that's the case, what would be the space consumption? Well, you have n, well, I would say big O of n, right? Edges per level, right? Okay, per level, because you have n points, right? Every point has a constant number of edges, right? But you have how many levels? You have h plus 1 levels, right? So, and therefore the space consumption is bounded by n times log delta, right? Don't forget h is log diameter, right? So diameter and delta, so there's only a factor of 2 difference there, right? Okay. So I still have to prove to you that every point at every level can only have a constant number of children, all right? But this is really, really boring, tedious, because at this point, I guess you should be able to do it, right? Because this is metric space, metric space, there's this doubling dimension. Why do you want doubling dimension in the first place, right? So you want doubling dimension because doubling dimension comes with this aspect ratio lemma, which can help you, right? Okay, so that must be the lemma you want to use, right? So indeed, so let's look at some arbitrary y. This is from, let's say, yi, okay, level I, right? So you look at all its children, okay? So let's say the children is m plus y, okay? M plus is like neighbor, right? And plus means out neighbor, right? So m plus y. So first of all, you see the diameter of this n plus y, you can bound it, right? Because I know every child will have to be within distance 7 times to the power of I to y, right? So by triangle inequality, if you use y as the bridge, you know that every 2 children must be within a distance of how much? 7 times 2, right? So 14 times to the power of I, okay, within each other, right? So that's the diameter. But on the other hand, don't forget, this n plus y is a subset of another net. You see what I'm saying? It's yi minus 1 is a net, right? Okay, good. So if this is the case, you know that any 2 points there, right, will have to be separated. You see what I'm saying? Okay, so you know the inter-point distance, in n plus y will have to be at least how much? 2 to the power of I minus 1, okay? All right, good. Now you have D max and D min, so now you can calculate, you can bound the aspect ratio, which is at most 28, right? So we know in general, if the aspect ratio is A, and then this set can have a size at most A to the power of lambda, okay? So if lambda is a constant, A is a constant, and that's a constant, okay? By the way, it's a large constant. I'm not saying this is going to be something that's definitely going to work, right? But this is something in theory. It's like worst case bound, right? Hopefully, in practice, you will see something less than that. Okay. But anyway, so when lambda is a constant, okay, and then this number of children is a constant. Okay, so this proves the space bound. Okay. Sorry, I'm recovering. Okay. All right, so now let's analyze the query guarantee, all right, approximation guarantee. First of all, look at the query time. Query time is super simple now, right? You descend h plus 1 levels, right? So at each level, what do you do? How much time do you need? Yeah, so just the number of children of the guy you're looking at, right? But we just proved, right? The number of children is always bounded by a constant. So that means constant per level, right? So all good. Well, if you look at the query time, clearly the query time is, big O of h, right? So this big O of h is simply log delta, right? So this is the query time. All right, so what remains is to show that this algorithm has a bound on the approximation ratio, right? So I promised 3, okay? So I'm going to show you why this algorithm achieves approximation ratio of 3, okay? So for that purpose, let me use P star to denote an actual nearest neighbor of Q, okay? And anyone, okay? Because you could have multiple nearest neighbors, right? Anyone would do, okay? All right, and then as I said, we descend a single path, right? So this path, let's say this is the access path. Okay, so this access path starts from the root and it ends at some point from y0, right? So we can further define this access path to be, say, a small yh, small yh minus 1, and then all the way to y0. Okay, so in other words, yh is the root. Yh minus 1 is the best child of yh, right? And then so on and so forth, right? So I minus 1 is the best child of yi with respect to q, right? So you've got a path like that, all right? So this is the access path. Good. All right, so our goal is to show that, at least one guy, one yi, okay, at least one, okay, satisfies, okay, the distance from Q to yi is at most 3 times the distance from Q to P star. Okay, so that's what we want to show, all right? This is going to prove the claim, right? So still remember, right, I said after you have got this pi, you return the best one, on this path, right? So if I can show you, at least one of them meets the approximation ratio guarantee, then all good, right? Good. So let's do it. Okay, let's do it. All right. Now I'm going to define something that might look a little like magic at this point, right? So I'm going to define this J. All right, so this J, all right. So this J is the largest integer satisfying this inequality. Okay. All right, so this is the definition. Okay. Well, as I said, if this is the first time you see it, you must be wondering, okay, so why? I mean, what's the rationale behind this J? Okay, what's the rationale? All right. Not such an easy question to answer at this moment. All right, but I can give you a heads up though. Okay, so this is so that you can anticipate what will be coming your way later. Okay. So intuitively, you can think about it like this. Okay, so if this Q, think about the distance from Q to P star. You see what I'm saying? Okay. That would have to be like 2 to the power of something. You see what I mean? Okay. This is something may not be an integer. You see what I'm saying? But when I look at it, let's say R is the distance from Q to P star. You see what I'm saying? Okay. All right. So let's, for convenience, just think about this R as some power of 2. Okay. So if this is the case, and then Q and P star, there's nothing closer, right? So this is like if you draw a ball, right? If you have a ball centering at Q and with the distance of R, right? And then that this P star is the best guy within the ball, right? Okay. All right, intuitively, somebody will be able to capture P star. You see what I mean? Because, for the value of R at that scale, we have an R net. Okay, we have an R net, right? So this R net basically says for P star, somebody will, in my R net, will be covering this P star. You see what I'm saying? Okay, good. So if this is the case, and then, I should be able to see some guy, and that guy, its distance to Q, sort of like 2R, right? So it's not too large. You see what I'm saying? Okay, good. Well, if this is the case, and then, I should be able to see some point, okay, some point that is reasonably close to Q at this level. Okay. All right. Well, this is a normal case, right? However, if you realize that this is not true, and then something is very wrong, okay, that's the intuition at this point, okay? When something's not true, and then it means that this query, its distance has some peculiarity, okay? And this peculiarity will be utilized later in the analysis, okay? So at this point, I would like to give you, this heads up message, all right? But anyway, so I hope now, if you look at this value of J, it's no longer that mysterious. Okay, so this is simply saying, well, I would expect if everything goes normal, I would expect, in your net, okay, in your net, you must have somebody that's able to capture me, at the level of 2 to the power of J. Okay, I would like to set this threshold to be 3 times to the power of J. Okay, and in particular, I would argue that, for the path that you descend, okay, so the level J, this Yj, will have to be able to capture me. If that's not the case, something goes wrong, okay, and that will have to tell me something about the distance from Q to this P star. Okay, all right. All right, so this is a heads up message, okay? In the end, I will come back to this message and I will help you understand it better. Okay. Well, first of all, let's look at one very important corner case. So if I define this J like this, it may not exist. You see what I'm saying? Okay. Well, if it does not exist, I will, let's say, if I want to be totally correct on this definition, I should say, if you do not find any such J, okay, and then you define this J to be nil, all right? So if no such J exists. Okay, so let's first consider the case where this J does not exist, right? So let's think about what happens if J does not exist. Well, this means, Qyi is less than or equal to 3 times 2 to the power of I. At all the levels. You see what I'm saying? Okay. So as I was saying, think about the heads-up message I gave you, right? So think about the distance from Q to P star. Well, if it was something large, you see what I mean? Let's say if it was like 2 to the power of 5, something like that, 32, right? If that is the case, as I explained earlier, right? So in my 32 net, I should be able to have something that's reasonably close to that query, okay? And by using a good algorithm, I should be able to find, some point to be within a distance at the level of 32 to the query, okay? And that distance threshold turns out to be 3 times 32, okay? So this is something I will guarantee later, okay? So intuitively, if you see that this did not happen, you see what I mean? Okay, because all the way down, you can always find some guy that is within this good threshold. So this query is always covered, okay? And then this means one thing. This means that the query could be very close to one of the points. You see what I mean? Okay, intuitively. Okay, the query could be very close to one of the points. So I will show you that in this case, Y0 is definitely P star. It's definitely a point that can be returned as the exact nearest neighbor. Okay, so that's the idea. Okay, all right. So this is the goal. Okay, so we will prove that the distance from Q to Y0 is definitely the distance from Q to P star. All right, so this is something we will prove. Okay. All right. Well, let's prove it. Okay, let's prove it. Well, you think about Y1. So Y1 is something that you accessed, remember, right? So this is the point that you access at level 1, right? Okay. And think about all the children of Y1, right? You must have calculated the distances from all those children to the query point, correct? So if I can prove to you that, this P star must be a child of Y1, and then what's the implication? The implication is that, you must have seen P star in your algorithm, right? So P star is the best you can have, right? So if you do not choose P star, you choose somebody else, and then that point must be as good as P star. You see what I'm saying? Okay. All right, so this is the goal, right? So if I manage to prove this, and then it implies that, this Y0 will have to be a nearest neighbor, right? Exact nearest neighbor. All right, so how do I convince you that P star must be a child of Y1? Sorry about that. How do I convince you? Well, by definition, you see what I mean? Okay. P star definitely belongs to Y0, because I told you before, Y0 is a very special level. right? So every point in the data set belongs to y0, right? So I have to show you that there is an edge from y1 to p star, okay? So that p star is a child of y1, right? So it suffices to show you, well, look at the direction of the arrow, right? So it suffices to show you the distance from y1 to p star is less than or equal to 7 times 2 to the power of 1. Okay, because that's the magic threshold that I used to decide, what should be the out edges of y1, correct? Okay, so this is my target, okay? So now I will try to bound this distance from y to p star, okay? So I'll use Q as the bridge to apply triangle inequality, okay? So this is correct, right? Well, you can see p star, since p star is a nearest neighbor, and then its distance to Q must be bounded by the distance from Q to Y, right? So this is at most 2 times distance of Y to Q, right? Okay. But as I said, right, so this query is properly covered at every single level, right? So what I meant by properly covered, 3 times to the power of I, right? So this means this is less than or equal to 2 times 3 times 2 to the power of 1. Okay, because Y is a point at level 1, right? So now you can see this is 12. Okay, 12. Okay, and our goal is 14. Okay. So now I have proven that this P star must be a point, okay? Must be a child of Y1. And you told me you accessed Y1. And therefore, the algorithm must have seen P star during its execution, right? And therefore, you must be able to return an exact nearest neighbor. Okay. So this is the case where, this point is properly covered at every single level. So you can see if that happens, and then this means that the distance from the query to its nearest neighbor must be very small. Okay. So later on, you will see when this is not the case, something will have to go wrong, as I said in the heads-up message, right? So as I was saying, let's say this is the query point Q, and let's say your P star is here, right? So your distance is R, and R is quite big. You see what I mean? Of course, we don't know what the value of R is, right? However, you think about it, right? So in the greedy algorithm, we descend all levels, right? So eventually we will go below R. You see what I'm saying? We will go below R, right? So as I was saying, the heads-up message, you will go below R, right? So when we get to a level whose distance granularity is much less than R, you saw something's going to go wrong. You see what I'm saying? You know what I mean? Because as I said, right, if we have not departed from R too much, let's say we're at R or even larger than R, and then I was saying, right, so at this level R, I expect to see another point that covers P star, and this point cannot be too far away from this Q, right? And therefore, that point to this Q should be quite close, and this close is at the level, at the granularity of R, right? And therefore, I should not be able to see like 3 times 2 to the power of j. You see what I mean? Okay, so if that happens, it indicates something's wrong. As you will see, what this means is that we have gone below this distance r. Okay, and then we must have already seen something that's close enough, right? So that's going to be the idea. Okay, so now this is case 1, right? So we'll look at case 2 with the ideas I have given you. Okay, so for case 2, so this big case says J exists. All right, now let me give you the definition again. So J is the highest integer such that the distance from Q to Yj is larger than 3 times 2 to the power of j. Okay. All right. So once again, the intuition is I expect to cover you at every single level if your distance is small. Okay. To the nearest neighbor, distance is small, right? If this is not the case, and then something goes wrong, and then I will analyze it. So that's the idea, right? So when I say close, when I say cover, it's at the level of 2 to the power of j. Okay. However, it's not exactly 2 to the power of j. I have to allow myself some slack, right? So it turns out that the slack constant is 3. So that's the idea, right? Hopefully this value of j is no longer that mysterious to you at this point. All right, so let's analyze. Okay, let's analyze. So case 2.1. Okay, so let's say j is h. Wow, j is h. So what does that mean, right? Okay, so this is another extreme example that allows you to see, to understand this heads-up message better. Okay, so basically saying, this yh here, okay, and 3 times 2 to the power of h, 2 to the power of h is even larger than the diameter of the data set. You see what I'm saying? So this is like, if all the points are in here, and then the query is really, really far away. You see what I mean? Okay. Now think about the heads-up message, right? By the way, why do I emphasize on the message so much? Because this will give you the main rationale for the final case, right? So as I said, right? So if the distance from Q to your P star is something small, and then something goes wrong here, right? Because I expect to cover every single point at every distance level, right? And therefore, I should have something that is quite close to your query point, right? Okay, but as you can see, this is so large. I mean, this is like even greater than 3 times the diameter, so far away from the entire planet, right? All right, so then there must be one possibility. Even the P star, even your nearest neighbor is very far away from you, right? So that's the intuition, right? So that's what I meant by something goes wrong, right? So that's the direction we will prove, right? So indeed, as you can see, we first argue that Q YH, right? So this is greater than 3 times 2 to the power of H. So this is at least 3 times the diameter, right? Okay. All right. So using this, we can argue that the distance from Q to P star is very large. How do we argue this? Well, this time we use triangle inequality in the negative sense. Okay. So this is triangle inequality. Okay. So we know the first term, right? The first term is at least 3 times the diameter, as I just proved, right? So the second term, subtraction, right? The second term is bounded by the diameter, right? And therefore, I have got this. So that gives me 2 times the diameter. You see what I mean? Okay. So this tells you, indeed, this confirms our intuition, right? Something goes wrong. All right. So you cannot, if you estimate the distance from Q to P star to be something very small, then something goes terribly wrong here, right? So it tells you, no, it's very large. It's 2 times the diameter. Well, if that is the case, and then I argue YH is a good point. Okay. Actually, it could be that any point in the data set would be a sufficiently good point. But we need something stronger because I said on the path that you access, on the path you access, right? You must have some good point, right? So I would say you only have to access the root. That's what I'm saying, okay? So now I argue that this YH must be something good enough. Okay, so I apply triangle inequality. Okay, so once again, the second term is bounded by the diameter, right? Because P star and YH, they are 2 points in the data set, right? Okay, so you already know the diameter is at least, the diameter is at most d qp star divided by 2, right? So now I can write. So this 1/2 of dq p star, right? So this is from the previous inequality, right? So now this is 1.5. You see what I mean? 1.5. All right. So you can see YH is not only a 3 approximate nearest neighbor. This is 1.5 approximate nearest neighbor, right? So even better. Okay, good. Okay, so this is case 2.1. Okay, case 2.1. Now, finally, let's look at the real case, right? So this is the final case. So case 2.2. Okay, so now with all the intuition I have given you, you should be ready to understand case 2x2. So case 2x2 says J exists and it's not H, all right, something less than H, right? So once again, what is J? J is highest integer such that the query is not properly covered. You see what I mean? Qyj, this is greater than 3 times to the power of j. Something must be wrong here. Okay. Yj, still remember Yj? So that's a point that you access on the access path, okay? All right, so we know 2 things. We know, first of all, this dqyj, by definition, this is greater than 3 times to the power of j, okay? So this is by definition of j, all right? But we know the query was properly covered at the level up. You see what I mean? Like j plus 1, right? So I know that, you know, at the previous level, this is still fine. You see what I mean? So this says a lot, don't you feel? This says a lot about the distance from Q to its nearest neighbor. Okay, because the reasoning, once again, I think I've given the reasoning several times, right? If it was something at the level of, let's say, to the power of j, right? Then I expect to see some guy to cover it, right? Okay, but no, you see, it's not properly covered, right? So what's going on here, right? Indeed, something's telling you, you know, this is, you don't have to go any further, actually, okay? So I will show that, you know, yj plus 1, so this is the last point that you accessed at the good levels where nothing was wrong. You see what I mean? That one is good enough, okay? That one is good enough, okay? So I will show you that qyj plus 1, this is less than or equal to 3 times q p star. Okay, so I will show you why j plus 1 is a 3 approximate nearest neighbor. You see what I mean? Okay. So by the way, if you look at the path, right? So this is level H, and now you get down to j plus 1. So the blue part is normal. You see what I mean? Okay, now something goes wrong. And J, you can see that the query is no longer properly covered, right? So now we return the point at level j plus 1, the blue one, okay, the good one, but the last point at the good levels. Okay. So if I have to show this, it suffices to show you what I said, right? So the distance from Q to P star will have to be at least 2 to the power of j plus 1. You see what I mean? So this is to formally tell you what this heads-up message really is, right? So I have said again and again, right? So if you assume that the distance from Q to its nearest neighbor is too small, and then something must be wrong. I mean, you should not be having this, you know, oddity here, right? So, you know, it's at this level, you don't have anything to cover it properly, right? Okay, and indeed, as you see, this is what we're going to prove, right? So the distance from Q to P star is actually at the level of j plus 1, okay, to the power of j plus 1, all right? So if I can show this to you, and by combining 1 and 2, okay, by combining those 2 inequalities, and then, you know, you should be convinced that yj plus 1 is a 3 approximate nearest neighbor, okay? So this is what I aim to show next, okay? All right, good. Now I think we are ready for the final argument. Okay. So what I'm gonna do is this. Okay, so I look at this. So I zoom into here. Okay, I zoom into here. So now you see this is yj plus 1. All right, and then I have yj here, right? So this is what's going on, right? Okay. Now I look at yj. Sorry, I look at this big yj. You know, this small yj is in big yj. Yj is the net, all right? What is the r value? 2 to the power of j, okay? Good. So by the covering property, I know that some guy will have to cover yj plus 1. You see what I mean? Yj plus 1 is the good guy there, right? So let's say z is a point in this net to the power of j net, okay? Satisfying the condition that, you know, p star and z is bounded by 2 to the power of j. Okay. All right, this just like I said, right? Every point will need to have some point within to the power of distance to the power of j in this net, right? So I said yj plus 1 needs to have 1, right? It turns out that, you know, I do not need that. Okay, I need the point that covers p star. You see what I mean? P star is a data point, right? So in this net, yj, there must be a point covering this p star. So that's what I need, okay? That's what I need. All right, so I'm going to argue. You know what I'm going to argue? I will argue that z must be a child of yj plus 1. Okay, so this green part is something we don't have yet, but this is something I will argue. You see what I mean? Okay. All right, so let's prove it. All right, so let's prove that z is a child of yj plus 1. Z is a child. So you already know how to argue for this child relationship, right? Because you know how we build the edges, right? How we build the edges, right? So if this is what you want to argue, you know what to prove, right? So you have to prove that this z and yj plus 1 is less than or equal to 7 times 2 to the power of j plus 1, right? So this is what you have to prove, right? So if you can argue that this is true, and then I'm convinced, right? So z will have to be a child, right? So how can I do this? Well, we can do this. Okay, let's see. Triangle inequality, okay? So this is less than or equal to p star, you know, and then p star to yj plus 1. All right, so this is using it once. Now let's use it again. Now this time we're going to break the second term into 2 terms by using q as the bridge. Okay. All right, so we know p star is, you know, an exact nearest neighbor, right? And yj plus 1 just some random guy, right? So we know the second term is bounded by the third term, right? So now we can have this. J plus 1. Okay. All right, so what this means is, you know, now we can apply what we know, right? So what do we know about the distance from z to p star? Well, that's from covering. That's from the definition of z, right? Z is the guy in the net that covers p star, right? And therefore, the first term will have to be bounded by 2 to the power of j. All right, now for the second term, we need inequality 1. You see what I mean? We need inequality 1 because by definition, that's still normal. That's a normal case, right? So the query point was properly covered, you know, in that case, right? So we know this is 2 times 3 times 2 to the power of j plus 1. You see what I mean? So this is like 2 to the power of j plus 6 times to the power of j plus 1, right? But we need 7 times to the power of j plus 1, right? So we actually get strict inequality here. So that's why I don't think you can improve on the constant C, all right? So yeah, but I don't care too much about a constant today, okay? All right, so here we have successfully argued that Z is, a child of Yj plus 1, okay? This is very useful because we know that, your algorithm must have seen Z, right? Because you were at Yj plus 1, right? You must look at all the children. So you must have seen Z. And you opted for Yj, right? You chose Yj. So that means one thing. Okay, so that means this Yj will have to be no worse. Will have to be no worse than Z. Okay. All right, good. All right, so we already know that this QYJ, now look at inequality 3 here, okay, inequality 3. So Yj is the abnormal case, right? So this is by definition of J, right? So we know QYJ is actually quite large. And therefore, we know QZ is quite large, okay? QZ is actually quite large. Okay, now I'm going to argue that, the distance from Q to P star is actually quite large, right? This is actually very intuitive already, right? Because Z is very close to P star. That's the best point for P star, right? In the cover, right? When you talk about the granularity here, right? The 2 to the power of J plus 1, right? Okay, 2 to the power of J, sorry. Okay, so now I can argue that the distance from Q to P star must be quite large. Okay, so we apply triangle inequality, the subtraction form. Okay, so this is triangle inequality, right? So look at it, right? So this is correct, right? So the distance from Q, the first term, distance from Q to Z, this is strictly larger than 3 to the power of 2. I mean, sorry, 3 times 2 to the power of J, right? But on the other hand, the second term, subtraction term, right? So this is upper bounded by 2 to the power of J. You see what I mean? So this is upper bounded by 2 to the power of J, right? So now you have 2 times 2 to the power of J, and what is that? That's precisely 2 to the power of J plus 1, and that's what I need in inequality 2. Okay, all right, so that completes the proof.